Okay. Last class I started with biotransformation. We discussed the very basic things about biotransformation. So biotransformation is nothing but it is the another name for biotransformation is metabolism. So what is metabolism? Metabolism is the process by which the drug molecule in its original form is converted into another form with the help of some enzyme. It's a kind of enzymatic reaction. So there are three cases which we have discussed in the last class. So after metabolism, okay, the product of metabolism is called as metabolite or metabolites, right? So why actually this process is taking place? So we know why the absorption is taking place. We know why the distribution is taking place. Why this metabolism is taking place? Why the drug molecule is converted into another form? What does it mean? So already we discussed this point that so actually the drug molecules will be having more lipid solubility comparing to the water solubility. The lipid solubility of the drug molecule will enhance the molecule to get enter into the cell to reach the target site. So since the molecule is more lipid soluble, it will be having less water solubility. The less water soluble molecule cannot come out of the body easily through the excretion. So to convert the more lipid soluble drug molecule into more water soluble molecule, which enhances the excretion, there is a process going on called as drug metabolism, right? So the major site of drug metabolism is, as we discussed in the last class, it is the liver, but not only liver. There are other other places in the body where this metabolism can takes place. So what's the role of drug biotransformation? So as we discussed in the previous class, so the process is taking place to inactivate and detoxify drug molecules, not only drug molecule, any foreign compounds which enter into the body, they should be inactivated or detoxified. Okay, otherwise they can harm the body. So that's why there are many enzymes which participate in inactivation and detoxification of the drug molecule. So after the metabolism, the drug metabolites, which are normally more water soluble than the parent molecule, so they can easily excreted by kidney. So far, this is what I discussed in the last class. Any doubt up to this, I can clarify. Any doubt up to this?
What is xenobiotics, sir?
Any foreign compound is called as xenobiotics. So bacteria, virus, any particle which is not part of our body. Okay, so all the molecules which are present in our body is called as endogenous molecule. Other than that, if any compound, any particle that enter into the body, they are called as xenobiotics. So drug molecule is not part of our body. We take it exogenously. The molecule is not synthesized within our body. The viruses, bacteria, somehow they can enter the microorganism. They are not part of our body. They are called as foreign element or xenobiotics. Understandable?
Yes, sir.
Yeah. So any other questions so far? I just cover very few points related to biotransformation. Any doubt up to this? Okay. Since no response, I assume that there are no doubt. So this point also we discussed in the last class, just refreshing the concept. So the drug molecule after the metabolism, there may be three cases or scenario. The first scenario is that the drug molecule is in its active form. After the metabolism, the metabolite is inactive. It's a very common. Often this takes place after the metabolism. The metabolites will be inactive. Most of the cases, right? But there are cases in which the active drug molecule after the metabolism, the metabolites will also be active. That is also possible. So, very rare cases. Initially, while taking the drug molecule will be in its inactive form. After the metabolic conversion, after the biotransformation, after the metabolism, the inactive drug molecule will be converted into active drug molecule. The inactive form of the drug molecule is called as a prodrug. Very important question for university examination. What is a prodrug? There are certain drug molecules which we take as inactive drugs. Once if they enter into the body, they undergo some kind of enzymatic reaction which converts the inactive drug molecule into the active drug molecule. So these are the three possible cases or scenarios or the endpoint of the metabolites. Is that understandable?
Yes, sir.
Yeah. So moving further, so here I have some example for the point which I discussed here, the cases, right? So as I said in the previous class, I'll be giving some example. These are the examples. So first we will take active drug molecule. Say for example, if you take paracetamol. Okay, so many times we use this term paracetamol, drug name paracetamol. So initially the molecule is an active drug molecule. Okay, the metabolite is not active, but the metabolite is, it can produce some toxic effect. The metabolite of paracetamol is N-acetyl para benzoquinone imine. So this is one of the metabolite of paracetamol, okay, which is inactive. The active form of the drug molecule and inactive form of the metabolite. No need to much worry about the toxicity, right? So it's a metabolite. N-acetyl para benzoquinone imine is an inactive metabolite of paracetamol. So coming to other example, no prodrug. So if you take zidovudine, okay, so this is one of the very famous antiviral drug molecule, very specifically used for certain types of viruses. Even this molecule is prescribed for HIV, human immunodeficiency virus. Very famous, right? So very famous drug molecule, antiviral drug molecule. So initially, while taking this drug molecule, the zidovudine is in its inactive form. It is in its inactive form. So once if you taken the drug molecule, so some enzyme, okay, phosphatase enzyme will convert the zidovudine into zidovudine triphosphate, and the triphosphate form of this zidovudine, it is the active form of the drug molecule. It is the active form of the drug molecule. Okay, so this is example for prodrug. Initially, the drug molecule is in its inactive form. So after enzymatic conversion, it is converted into active form. Okay, so another example is if you take diazepam. So initially, the drug molecule in its active form. So the metabolite of this diazepam is nordiazepam. Then it is converted into oxazepam. So we can say that nordiazepam and oxazepam, they are consecutive metabolites of diazepam. Okay, so initially the drug molecule is in its active form. Also, the metabolite of the drug molecule is also in its active form. Okay, so these are some examples of the cases which are explained here. Initially, the drug molecule in its active form, metabolite is inactive. Initially, the drug molecule is in its active form, metabolite is also active. Prodrug, initially the drug molecule is in its inactive form, the metabolite is active. Right? Some examples, right? So we can give many examples. These are few examples. So first pass biotransformation, first pass metabolism, we already discussed, right? So while discussing the absorption, because this topic is related to absorption, right? The first pass effect is going to determine that how much amount of the drug molecule will enter into the systemic circulation. So that's why we studied the same concept there itself, right? So anyway, since we discuss biotransformation, so I am going to repeat the same thing again, right? So we have two types of circulation. One is called as a systemic circulation. Another one is called as the portal circulation. So this is hepatic portal vein. So if you take the oral drug molecule, the oral drug molecule first enter into the stomach. Okay, so we swallow the oral drug molecule, enters into the stomach. So through stomach, right? So the molecule should enter into this hepatic portal vein. So the drug molecules are entering into the hepatic portal vein. Okay, so they are entering into the circulation, but this is not systemic circulation. This is a hepatic portal circulation. So from this hepatic portal circulation, the molecules slowly enter into an organ, first organ. Okay, the drug molecule reaches the first organ, that is the liver. Liver is the first organ to which any of the oral drug molecule should reach. So liver is the major site of biotransformation. We know that because it is having an enzyme called as cytochrome P450. CYP450 is the enzyme. So biotransformation, this CYP450 which are present in this liver, its main job is the drug molecule act as substrate for this CYP450 and convert the substrate molecule into product. So drug molecule is the substrate for this CYP450. So it takes the CYP substrate molecule, drug molecule, and convert the drug molecule into product or products. So the products are the metabolites. Okay, so some proportionate of the drug molecule will be metabolized in the liver, and that is what is called as the first pass effect. And the remaining drug molecule will enter. Not 100% of the drug molecule will be metabolized. Okay, so some proportionate of the drug molecule will enter into the systemic circulation. The concentration of the drug molecule that is present in the systemic circulation is called as, what's the name for that? The concentration of drug molecule present in the systemic circulation is called as, what's the name for that?
Bioavailability.
Okay, that is what is called as the bioavailability. The bioavailability of the drug molecule is mainly determined by the rate of absorption and the first pass effect. If the absorption is good and less amount of first pass effect is absorbed, then that will favor the bioavailability. Bioavailability will be more. If the rate of absorption is bad, less, and more amount of drug molecule biotransformation is taking place in the liver, if the first pass effect is more, then the bioavailability of the drug molecule will be very less. Is that point understandable?
Yes.
Okay, that is what is called as the bio. That's called as the first pass biotransformation, right? Okay, so coming to the main concept of biotransformation, so we discussed the factors which affects the absorption distribution. So like that here, biotransformation, basically we can classify the biotransformation into two stage or two phases called as phase 1 biotransformation and phase 2 biotransformation. Again, I repeat, this biotransformation, we can classify this biotransformation into two phases. Phase 1 biotransformation and phase 2 biotransformation. So phase 1 biotransformation, both phase 1 and phase 2, these are enzymatic reaction. Okay, phase 1 enzymatic reaction, create or unmask a chemical group required for phase 2 reaction. What does it mean? It means that once if the drug molecule undergoes phase 1 biotransformation, okay, that molecule, that metabolite is now ready for the phase 2 metabolism. Happens sometimes sequentially. Phase 1 prepares the drug molecule, okay, for phase 2. So the metabolites created in phase 1, now it moved to the phase 2 metabolism. Not always. Some cases the drug molecule, it may bypass the phase 1 biotransformation and directly go to the phase 2. Again, I repeat, it is not necessary that it should happen sequentially. There are some cases in which drug molecule may bypass the phase 1 metabolism. It can directly go to the phase 2. But in most of the cases, the drug molecule will first undergo the phase 1 biotransformation, and the metabolite of the phase 1 biotransformation will go to the phase 2. The metabolites of phase 2 biotransformation, they can easily get excreted from the body. The another cases, sometimes the molecule may not undergo the phase 2, it may undergo only the phase 1. So after the phase 1 metabolism, the drug molecule may directly get excreted. All the situations are possible, right? So moving on further, this is a quite simple example. I request you to remember this example, memorize this example for examination point. Very simple example. So far our understanding is that metabolism is a biotransformation process which mainly takes place to enhance the excretion. Because the drug molecules are more lipid soluble, they cannot easily dissolve in water and get excreted from the body. In order to facilitate the excretion process, the drug molecule undergoes biotransformation. The more lipid soluble molecule will be converted into more water soluble. So here I have chosen aspirin as the example, because aspirin, we discussed about the molecular mechanism, we discussed the structure of aspirin. So can you tell what are the various functional groups which are present in aspirin? We have COOH. What's the name for that functional group? The COOH.
Carboxylic acid.
Carboxylic acid group is there. What's the name for this functional group? Anybody? What is the name for this functional group? OCOCH3.
Ester.
Hmm? Ester, right? Okay. Ester functional group is there. Carboxylic acid functional group is there. What's the name for this functional group?
Phenyl or benzene.
Phenyl or benzene. Okay, benzene or phenyl. Anything is right. So aspirin is more towards water soluble or lipid soluble? Just by looking at the structure, you know which functional groups favors the water solubility, which functional group favors the lipid solubility. So can you tell whether this is more towards lipid soluble or water soluble? Yeah, somebody can answer.
Lipid salt.
Okay, it is more towards the lipid soluble. Okay, so whenever you have this ester functional group, they actually enhance the lipid solubility. Also, the phenyl ring. So only water soluble group is this OHCOOH, carboxylic acid group. But comparatively, this is more towards the lipid soluble, because more functional group contribute for the lipid solubility. So which means that this molecule can it is good for this molecule to get absorbed. Okay, absorption will be good, but very poor excretion. Very poor excretion because of the lack of water solubility. So the drug molecule, it can undergo oxidation reaction or hydroxylation reaction or dealkylation reaction, deamination reaction, hydrolysis. Any of this reaction can take place in phase 1. Okay, so we classify the biotransformation into phase 1 and phase 2. Common phase 1 reactions are oxidation, hydroxylation, dealkylation, deamination, hydrolysis. So any of this reaction can take place. Even one or two can take place, doesn't matter. So after this reaction, right? So this is after phase 1. So we can say this is metabolite. This is a metabolite of aspirin after phase 1. So what happened? This ester group is converted into alcohol group, OH group. Ester is now converted into alcohol. Now, if I ask a question, if you compare aspirin and salicylic acid, can we say that salicylic acid is slightly more water soluble than aspirin?
Yes, sir.
Yes, right. So because of the replacement of ester group into the more water soluble OH group. Okay, this is salicylic acid is one of the metabolite of aspirin. Now what happened? Salicylic acid is not completely soluble in water. Still, it cannot easily excreted from the body because for the excretion, renal excretion, right? So we need almost complete solubility of the drug molecule in water. So the metabolite of phase 1 reaction is now taken to phase 2. Again, so enzyme which takes the salicylic acid, and most of the reaction taking place in phase 2 reaction is the conjugation reaction, not oxidation, hydroxylation, dealkylation, deamination or hydrolysis. These are part of phase 1. In phase 2, the most important reaction is the conjugation reaction. Conjugation. So what is meant by conjugation? So if this is your metabolite, okay, so it take some water soluble compound which is already present in our body and conjugate that with the metabolite. So this will be the resulting product. What's the ultimate purpose? Since it is conjugating a highly water soluble component to the metabolite, now this metabolite will be very high water soluble compound comparing to the metabolite of the phase 1. So what's going on here? So it takes endogenous molecule, endogenous molecule, glucuronide. It is an endogenous molecule, glucose family. So it takes, so this is glucuronide. So if you look at this structure alone, so can we say whether it is more water soluble or lipid soluble?
Water soluble, sir.
It is more water soluble. This more water soluble component is already present in our body. So now this enzyme participating in phase 2 takes the salicylic acid and attach salicylic acid with this glucuronide, more water soluble component. So now as a whole, this is considered as the metabolite. This is considered as the metabolite of phase 2 reaction. So now this metabolite is having very high water solubility. So this molecule, the conjugated glucuronide form of salicylic acid, now can easily excreted from the body. Is that understandable so far?
Yes, sir.
So this is why actually the biotransformation process is taking place. One more point I add: any exogenous molecule, any xenobiotic that enter into the body should come out of the body. Okay, it should not permanently stay inside the body. If it stay inside the body, then it will produce a lot of side effects or undesired effect. That is the purpose of the excretion process. Is that understandable?
Yes, sir.
Yeah, okay.
Yes, sir.
So moving further, so we're going to see that which reactions are part of phase 1 biotransformation and which reactions are part of phase 2 biotransformation reaction. So mostly the phase 1 biotransformation reaction includes oxidation, hydrolysis, reduction. The very common, very common reaction in organic chemistry: hydrolysis, oxidation, reduction. That is what exactly taking place in phase 1 biotransformation, right? So as I said that these reactions are mainly carried out with the help of a family of enzyme called as microsomal cytochrome P450 monooxygenase system. Very important for understanding the entire story of biotransformation. It's microsomal cytochrome P450 CYP monooxygenase system. So this is a family of enzyme that is mainly present in liver, not only in liver, mainly present in liver, that is responsible for the biotransformation of the drug molecule. That is what I given here. Family of enzymes that catalyze the biotransformation of drug, a wide range of chemical structure. Very important thing is its specificity and selectivity. They have selectivity, specificity for wide range of chemical structure. That is the reason why many drug molecules can be easily get metabolized by this family of enzyme. So what are the component? Okay, so how it is made? Okay, what makes this microsomal cytochrome P450 CYP? So this is having CYP, hemoprotein. CYP, hemoprotein. So hemoprotein is a protein which contains a metal, specifically the iron. Hemoglobin, okay, hemoprotein. So these are same family, hemo, which means metal containing, metalloprotein, specifically the iron. It is a flavoprotein that is reduced by nicotinamide, adenine dinucleotide, phosphate, NADPH, NADPH, and membrane lipids in which the system is embedded. Right? No need much worry about that. We are going to see the mechanism. Before
Sir,
seeing the yeah,
this
yes.
particular enzyme is for both phase 1 and phase 2, sir.
Cytochrome P450 is the family of enzyme that is in both phase 1 and phase 2.
Okay, sir.
But
Only these enzymes
mostly
are involved.
one this is mainly involved in phase 1. Okay, we discussed about the conjugate. Yeah, it's involved mainly in, yeah, both phase 1 and phase 2. Doesn't matter. Yeah.
Okay, sir.
Okay, this oxidation reaction, this reduction reaction, all this takes place with the help of the cytochrome P450 enzyme. Any questions up to this? I hope I answered your question right.
Yes, sir.
Yeah. Any other question from any other student so far? Okay, since no response, I assume that no question. So this is this slide. I have kept different isoforms of P450, cytochrome P450, and what are drug molecules which are very selective for that isoform of P450. CYP1A2, CYP2B6, CYP2C8, CYP2C19, and
Hmm.
so on.
Hmm.
So these are, you know, different types or different form of cytochrome P450, isozyme of P450, and the drug molecule, okay, that bind to the corresponding CYP450 is, if you take paracetamol, caffeine, if you take uh, tacrine. So these are drug molecules which goes and bind to CYP1A2 and metabolized. So on the other hand, if you take cyclophosphamide or methadone, so these are drug molecules. They specifically go and bind to CYP2B6, and this CYP2B6 which metabolize this drug molecule. So if you take uh, paclitaxel, repaglin, so these are drug molecules. They bind to CYP2C9 and so on. Okay, that means that there is no one enzyme. Okay, it's a family of enzyme whose main job is metabolizing the drug molecule. Is it understandable?
Yes, sir.
So what will be the difference between CYP1A2 and CYP2B6 or CYP2C8? So if you look at the structure of those, so mostly they'll be having very similar structure, but the binding site will have slight variation. Okay, that slight variation in the binding site lead for change in the specificity of the enzyme for different drug molecules. So for any questions? Any questions so far?
No, sir.
Okay, I assume that no questions. So this cycle is very important for the examination. So this is a common cycle which explain how actually the metabolism taking place. This is called as a P450 cycle. So in the previous slide, I have shown different types of different isoforms of cytochrome P450. Or any of that isoform will follow this mechanism for converting the more lipid soluble drug molecule into water soluble drug molecule. That's why it is called as a P450 cycle. It's a common cycle, irrespective of what isoform it is, right? So it's common for all the P450 enzyme. So we know that this P450, cytochrome P450, is a metal containing protein molecule, hemo, right? So specifically this hemoprotein, they used to contain iron as the metal, central metal ion. So what happens, so the drug molecule, okay, so it starts here. So this is the cytochrome P450. This is cytochrome P450, which contain the iron as the central metal ion. The iron, as you know, that can present in different oxidation state. So normally, in this protein, it is present in 3+ state. Okay, the central metal ion is present in 3+ state. The presence of the metal ion and the oxidation state of the metal ion is very important to carry out all the reaction within the binding site to convert the more lipid soluble drug molecule into water soluble. So here we have the drug molecule DH. DH denotes the drug molecule. So the drug molecule goes and bind to the cytochrome P450. Okay, so that is represented here Fe3 plus DH. Drug molecule is now attached to the P450 enzyme. That is how to understand. So after the binding of the drug molecule, so the electron is supplied to this protein. Okay, so electrons can be supplied to the protein molecule. The source of electron is coming from NADPH P450 reductase. This is another enzyme. Okay, that is the source for the electron, which is donating electron to this cycle to enhance, to help converting the lipid soluble molecule into more water soluble. So this cycle takes one electron and taking that one electron converts the Fe3 plus into Fe2 plus, one additional negative charge that converts the Fe3 plus into Fe2 plus. So how to understand this? The drug molecule is bounded to the binding site of this P450. So P450 is having Fe3 plus. So because of the uptake of the electron, the central metal Fe3 plus is now converted into Fe2 plus. Nothing happened for the drug molecule. The drug molecule is not providing the electron. The source of electron is completely different. That is NADPH P450 reductase. So then oxygen molecule, right? So our body, having oxygen. So oxygen is donated. Molecular oxygen O2. O2 is the molecular oxygen. Molecular oxygen is donated to the cycle now. So now the Fe2 plus drug complex is converted into Fe2 plus O2 drug. Very simple. It's taking the O2, right? So then, so the H plus and electron is again donated to this cycle. The H plus and electron is donated to the cycle. The source of electron, already we said that NADPH P450 reductase, and the source of H plus is coming from cytochrome B5. So these are two key player in supplying the electron and the hydrogen proton H plus. H plus is called as proton. So it is donating both electron as well as proton. Okay, so one hydrogen without its electron is called as proton. So it is donating the proton here. So that converts Fe2 plus O2DH into Fe2 plus OOHDH. Okay, so because of taking this H plus and E minus electron, So Fe2 plus O2 DH is converted into Fe2 plus OOH. So again, there is a removal of water molecule from this, so which converts Fe2 plus OOH DH. So water molecule will be removed here, so which converts this complex into FeO3 plus DH, which further converted into Fe3 plus DOH. FeO3 plus is converted into Fe3 plus DOH. So the resulting product is Fe3 plus is part of the enzyme. Okay, nothing to do with that. So DOH is the product. Okay, DOH is the product. So initially the drug molecule is DH. Now the DH is converted into DOH. DH is converted into DOH. So if we compare the water solubility of DH and DOH, the presence of this OH will improvise the water solubility of the drug molecule. So we can say that the more lipid soluble molecule is now converted into more water soluble molecule. That is what is exactly happening in this P450 cycle. Is that understandable?
So can you explain again the step of Fe2 plus OOHDH to FeO3 plus DH?
This one?
Yes, sir.
Okay, let me erase this. Okay, here it is Fe2 plus OOH. Okay, so here there is a donation of proton to the cycle. Okay, H plus is donated to this cycle. Okay, if H plus is donated to this cycle, so what's happening? This OH, okay, this part will combine with the hydrogen. So there will be a removal of H2O. This OH and this H, they join together. So they leave as H2O. Okay, so because of that removal of water molecule, the electronic rearrangement will takes place that changes the oxidation state of the ion, which will be converted into FeO. Okay, the complex with the oxidation state of 3 plus. So DH will be still there. Is that understandable?
Yes, sir.
Yeah, that is what exactly happening here. It's a very simple cycle. It involves just the oxidation reduction, nothing else. Okay. So this is
Yes,
very
sir.
important for examination point, and very important for understanding the concept how lipid soluble drug molecules are converted into water soluble. Is that understandable? If I show this, you can understand how this reaction is taking place. Correct? How this is taking place, you can easily understand, right?
Yes, sir.
Okay, the DH, so this is the DH form of the drug molecule, will be converted into DOH. Simple notation, right? So that is what's happening in biotransformation, right? So with the help of P450 enzyme.
Sir,
Yeah,
this whole cycle takes place in liver, sir.
you mean can it takes place in reverse?
No, sir. Does the cycle like fully takes place in liver?
Okay, liver. I thought reverse. This cycle is taking place in liver. It's mainly, this cytochrome P450 is present in liver. But wherever the cytochrome P450 is present, there it can take place. So can
So,
I
so in
repeat?
whichever organ the biotransfer.
Yeah, whichever organ there is a cytochrome P450 enzyme. where the metabolism taking place, all those places this reaction is possible.
Okay, sir.
But the major site is liver. See, the point is that I don't want
Okay, sir.
you to fix in mind that this is taking place only in the liver. That's why, I'm not confusing you. Mostly this reaction taking place only in liver. But there are rare cases it may also take place in some other part of the body where we have the cytochrome P450. Understandable?
Okay, sir.
But
Yes, sir.
major site is the liver. Okay, major site is liver. So shall we stop here today?